We're going to continue here and deal with three more topics, bring us to the end of the first boot camp for MATLAB. The first one is we're going to review the different program structures in MATLAB scripts or program code. And then we're going to take a look at plotting, different types of plots and how we can customize them to our needs. And then finally, we're going to review how to create separate MATLAB functions that we can use as the part of other scripts. And all of these features, we will make use of them when we go on to the Bootcamp 2, which will focus on problem solving. So I'm going to start here in the editor and illustrate one of the simplest program structures, which is formally called a selection structure and involves decisions. And often we call them if structures because they involve the use of the if statement. So let's start here with an input and put in a string, enter a value for x, and then I'll make a calculation with a variable I create SGN2, which is equal to x squared, okay? And what we want to do here is that we want to take whatever the sign of x is and pass it through to the value of SGN squared. And obviously, if I just square x, I'm going to lose the sign if it's negative. So I'm going to illustrate the use of a one-line, one-way if here, and that is if x is less than 0, and then a semicolon, and then I put in the statement SGN2 is equal to minus SGN2, and then semicolon and end, all right? And when you use a structure in MATLAB, you start it with a particular keyword like if here, and then you terminate it with the word end. And in the script, you can see that those are coded colored blue. So then we'll just use a DISB function and display our result, and that will be our script. I will save this, and I will call it one line if example. And because I already have one of these, I'll add the numeral 1 to this, and now I've saved the script. So I can execute the script from the command window, and more commonly, I can just run it here. And then it switches me over to the command window, and I can put in something like -2, and it shows me the -2, and then it shows me the 4 result. Now, the reason it shows me x equals -2, let's go back over to the editor, is because I didn't put a semicolon after that first statement. So if I do that and run it again and put in -4, it gives me the result of 16. Now, that doesn't look right, all right? So let us come back over and see what we've got going on here. I should have this here should be less than, right? If it's less than 0, we want to carry the sign through. And you probably already saw that. So let us run it again and put in my -4, and we get a -16. And you'll notice that if I use the up arrow a couple times, I can execute the function again, put in 4, and we get 16. All right? Okay, so that is the use of a one-line if. In other words, it's just a compact way to say, if something is true, do this. And you can actually put more than one statement in here before the end, but it becomes a little long-winded. So when we have more than one statement, we want to um, use multiple lines in the if. And so what we will do here is create another script, hit the plus sign there, and I will have an A equal to input, enter a value for A, and then I will put a B equal to input, enter a value for B. Okay. And then what I want to do, and this isn't that meaningful, but it illustrates the point, is that if A is less than B, I want to switch the values in A and B. All right. So I'm going to do a test and I'm going to say if A is less than B, semicolon, and then you'll notice that we get an automatic indent that's provided by the editor, and this helps us see the structure in the code, so we recommend it. And if it's less than that, I'm going to have a temporary variable take on the value of A, and then I'm going to have A be assigned the value of B, and then I'm going to have B be equal to minus the temporary value. So and then I'm going to back that up and put in my end. So what have I done here? I've said that if A is less than B, I want to switch A and B, but I want B to end up having the negative value that A had originally. So that's just an illustration. So let's display, and in brackets, I'm going to put A space B. All right. So let's run that. Well, you see it wants me to save this file before it'll allow me to run it. It's catching me on that. So uh, I will do, I'll just call it one way if example 1. Okay, enter a value for A, and we will first just try A as 4 and B as 2. And so since A is not less than B, it just keeps those values and displays them. So let's come up a couple with the up arrow and run it again. And let's put in 2 for A and 4 for B. And now what it does is it switches the 2, all right, and it negates the 2, all right. So when I started, B was a 4, so it took the A as a 2 and negated it, put it in B, and what was in B is now in A. Now, it's not that earth-shaking, that code, but it gives you an idea back over here of what a one-way if with several statements looks like. And you'll notice that we have if, and then we have what's called a relational expression here that evaluates either to true or false. We have a series of statements, and then it's terminated by the end statement. So we're going to go on with these selection structures or decision structures and illustrate a couple more. So we'll come over here and I'm going to try another one, all right? And I'm going to go back to my x equals input, enter a value for x. Then I'm going to have if x is greater than 0, then Lx is equal to log of x. Log here is the natural logarithm. But then I'm going to do something when x is negative. So that means I need, if x is greater than 0, do this. If x is less than 0, I'm going to say, otherwise do this. So the way you do that is with the else statement. And I say Lx is equal to the log of minus x. So if it's negative, the log would not be defined, logarithm, so I negate it and just compute the log for the positive value, all right, of x. And then I can terminate this. So here we have what we call a two-way if. We have one way of going positive, one way of going if it's negative, and then I'm going to DISP Lx, all right, as my final statement. And let us save this guy, and we will call it a two-way if example. Okay, so let's try to run this. And a value for x, if I do 2, it gives me 0.6931, which is the natural log of 2. If I go back with the up arrow and run it again and put in a minus 2, it still gives me the same value for that. Now, a little mystery here is what would, we checked for positive and negative, and what would happen if we put in 0 then? It gives me minus infinity, all right? So what happened here was that if it's greater than 0, do this. Otherwise, it's going to do this. So it's not greater than 0, so it's going to do this. And that would mean that it's going to take the log of minus 0, which turns out to be the log of 0, which is minus infinity, or what it thinks is minus infinity in its function evaluation. Now, one way of handling that is with something called multi-alternative if, all right? So let's take this code and let me do a save as and just change it from 1 to 2 here. And then I'm going to put in, instead of else, I'm going to put in else if x less than 0. And that covers that option. And then I'm going to have an else, which would be the case when it's equal to 0. So at that point, I can do whatever I want. I can just say, well, I'm just going to say Lx is equal to 0 for whatever that means. I'm going to save that. We're going to try to run that. And I'm going to put in 0, and it gives an output of 0. If I put in minus 2, it gives me what I had before. Okay? So that's a quick example of turning a standard if statement one way into a two-way if, all right? And then turning a two-way if into a multi-alternative if, okay? So I'm going to show you another example that I already have coded, I believe. I'm going to open a file here and see if I have a multi-alternative if file. I think I do here somewhere. It's called ClampX. You can open that too. And this is a similar thing, but it's a much more practical application that you can run into in a lot of process calculations. And that is what we want to do is we want to take a value and we want to clamp it between two limits. And if if it is outside those limits, we set it equal to the limits. And if it's inside the limits, we let the value go through. So similar type of structure here. We get a value for x. We see if it's greater than 1. We're clamping the value between 1 and minus 1. If it's greater than 1, we set the limiting value to 1. If it's less than minus 1, we set the value to minus 1. And otherwise, we just set the value to x. Okay? So that's called a clamping operation or a limiting operation. And if we run that, whoops, I'm going to put in something like 2, and it takes the value of 2 and makes it equal to 1. And then let's run it again, put in minus 10, and it limits it to minus 1. Let's run it again, and let's put in a value of 0.75, and it lets the 0.75 go through. So that is the multi-alternative if structure, all right? And then there's one other if structure that we don't use that much. It's called the select case structure, and it's quite often used in what we call menu operations. You'll notice that with the multi-alternative if it fails the first test, it goes to the second test. And if it fails the second test, it goes to the third or to the else and goes through. So there's a sequence here, all right? With the next structure, there's not a sequence. It evaluates all the alternatives at once and picks the one that works. So let's go and look at the code for that. And let me take out a couple of these. So I'm looking for something here that's called switch. There's something called switch examples, so I'm bringing that up. And here, the reason that I'm doing it this way is it's just going to take us a little bit too much time to type in this code. So I want to get it up here where you can see how we do it, all right? So what we've got here, or we've got a standard input statement to get us a temperature in degrees Fahrenheit. And then we have another input statement where we want the user to enter a letter, C, K, or R for Celsius, Kelvin, or Rankine. And so in order to have it accept a letter to be entered, we have to follow it with an argument of S in apostrophes, where the S stands for string, which means a text entry. This gives us a variable called UN, standing for units. And then what we do is we do a switch on UN, which is supposedly equal to either C, K, or R. And depending on which it is, it will do one of these three cases. All right. So the first case for C, take away 32, divide by 1.8, and then display the result. K, take away 32, divide by 1.8, add 273.15, and to convert it from Fahrenheit to Rankine, add 459.67. So it will do whichever of these cases is given by the letter that the user has entered. And if they don't enter the right letter, it's just going to go through the end of the switch statement. Now, there is the possibility of including what's called a case else, where you will put in whatever statements you want, such that that might have a corrective message for the user or whatever, because they didn't enter one of the correct letters. Another thing that you can do, we're not illustrating it here, is you can take the entry and make sure that it is in uppercase. So if they happen to put in a lowercase c, you can automatically use a function for uppercase and change it over to an uppercase C. So let's take a look at this particular structure and let's run it. And down here at the bottom, it says enter a temperature in degrees F. So let's put in 212 and enter C, K, or R. I'm putting in C, and so it tells me that the temperature is 100 degrees C. If I want to do it again, I can run it again. I can say 1200 degrees F. What is that in kelvins? And it's 922.04. Okay, so I can use the switch example in order to implement a menu type choice. It's sort of interesting when we go over to Excel and the VBA language, there is actually a select case structure using those words. And we go over to the Python programming language and it doesn't provide us anything for this. Okay. So let's go back to our slides now and review where we've been. And then we're going to go into what we call repetition structures, which are like looping structures. Okay, so back over to our slides. So this was our one-way if, and you can see how that lined up, and also I've included a name of the script file that has the statements. Here I typed them in because there were only 4 lines. Then we moved on to the one-way if with multiple lines, and you can see the structure here, what that looks like. And the example that we ran where it reversed the 2 and the 4. Okay, and so there's an example file for that. Then we expanded it and included the else clause. This shows our example there. And then I sort of fixed that up to accommodate 0, but I don't show that here. So that's what we had, and there are a couple of examples there. And then we come down to our multi-alternative if with the else if clause with our clamp function example. And this shows that and shows 3 examples where for the first 2, it's clamped to -1 and +1. And the third one, it allows -0.3 to go through. Okay, so that's what that looks like. And we then handled the switch structure. And in each case, I'm showing the general format for the statement and then showing a specific example, which is the one that we illustrated, and showing a couple of conversions. One in this case, -100 degrees, is 360 Rankine. All right. So that's what we have, and you've got the code there for that. And now what we're going to do is we're going to go on and we're going to look at repetition or looping structures. All right. And the first one of these we're going to look at is the for loop, which is called count controlled repetition. And the general structure of this is you do for a variable we call index here, can be any variable, start, colon, increment, colon, end. And if you leave the increment out, it's assumed to be 1. So if I have for index equals 1 colon 10, it's going to run this loop 10 times with the index shifting from 1, 2, 3, 4, etc. And then we can make modifications to this structure when called for. And the first is called the break option, where we want to get out of the for loop if a condition we're testing becomes true. So we can insert a statement that says if condition, that would be a logical condition that would evaluate to true or false, then break. So if it's break, it's going to continue after the end statement. If it's not true, it's just going to continue the loop. And we'll show you examples of these. And then the third is what we call the continue option. And this is for premature cycling for a loop. So we have a test in the loop that if it's true, it will just continue to the next cycle of the loop. If it's false, it will execute some statements before it does that. So those are the break and the continue options that are shown there in general format for you. Okay? So what we want to do is look at a couple of examples for this. So I'm going to come back over to my editor and I'm going to open a file that's called MAD1, M-A-D-1. So what we've done here, it's pretty obvious, is we've just entered an array of values for X that look like perhaps some measurements. In this case, they may be measurements of something like pH. And what we would like to do is compute the statistic which is called the median absolute deviation. Excuse me. So what the median absolute deviation, or MAD for short, is you compute the median of your values in the array, and then you compute the differences between your values and the median. Take the absolute values of those differences, and then you take the median of those absolute values and you divide it by a conditioning factor of 0.6745. So let's see how this does it with the code. The first is it calculates the median using MATLAB's built-in median function. And then it finds out how many measurements we have by using the length function to count the number of items in the X array. And then it sets up a for loop for I equal 1 to n, all right, which means it's going to use a counter, 1, 2, 3, 4, however many items we have. And for each counter, it's now using array subscripts. So it's going to take X sub I, which will be 1, 2, 3, etc., subtract it from the median, and take its absolute value with ABS and assign it to a new array called XDEV and the position I for that array. And then what we're going to have, once it's got the deviation, is it's going to take the median of those deviations in the deviation array, divide it by 0.6745, and assign that to something we called XMAD and display it. So the reason for using the 0.6745 as a statistical reason to have the MAD end up being approximately the same as the true standard deviation. And I'm not going to uh, go through the theory of coming up with that 0.6745, all right? And that's assuming the data are adhere to a normal distribution. So as we go through here, and let me bring this guy over here. Let me switch my windows a little bit so we can see our workspace. We come back to the command window and type clear, and clear the workspace, and then come back over to my code here. And what I'm going to do here is instead of just running this code, I'm going to go through it step by step so that we can see what's happening as the program executes. Let me make sure that workspace is cleared and start back here. Okay, so here we are. What I'm going to do, I'm going to start the code in single step mode by clicking this step button up here. Now it turns out that there is a shortcut key to this, which I can't use, but because it interferes with my recording of the screencast, but you can use it, and it's the F10 key. So if I click that, it will get ready to step and execute the first statement. And if I do that, it shows the result being creating this variable for x, the array of values. And then if I do it again, it shows that it's computed the median to be 9.85. And then we do it again and we come down to the start of the for loop and hit that once, and it creates a variable I over here with a value of 1. And then it's going to execute this statement, and it's going to come up with the first xDEV value, which is going to be 10.1 here, minus 9.85, and that's 0.25. Absolute value is still 0.25. It's going to assign that to xDEV, and then if I run through the loop again, it creates the next value of xDEV, and it just will build up these values. All right, and I can expand this over here to show that it's building the values of xDEV as I execute the loop. So that is how that works. And so if I'm ever satisfied that things seem to be working okay, I can just tell it to continue execution, and it will complete the calculation, and it's showing a MAD here of 0.4448. And since I'm displaying that, if I come back to the command window, we see that we have the MAD of 0.4448. So that is shows you an example, a simple example of the use of a for loop, and a very typical one where we take the index variable of the for loop and we use it as a subscript for arrays within the loop. Okay? Now, one thing, whenever you are doing something like this and it involves the use of arrays with indices, you want to, in MATLAB, look for the possibility to
um, to use vector matrix operations and have a more concise code than using for loops. So I'm going to show you an example of that now in the script that is called MAD2. And this calculates the exact same thing, but you can tell that it does it in a much more compact fashion because it gets the median of x, but then it uses a formula where x is a vector, x med is a constant, and it just subtracts the constant from all the array or vector elements, takes the absolute value of all of them, and assigns them to a new array called xdev. So we really didn't have to use a for loop at all. And then it calculates the MAD in the exact same way as before. So if I run this and take a look, we see that we get the exact same result. Okay? So we'll come back to the slides and review that in a little bit. But now what I want to illustrate to you is what it might look like if we used those break and continue commands. So let us go back to our editor here and get rid of a couple of these former examples and look for something which is an example of break. There's a file called break example. This is a very simple file. You could have typed it in, I suppose. But what it does is it's using an array here, which happens to be the early part of the Fibonacci sequence. And then note that there are 8 elements to this. So it sets up a loop for I equal 1 to 8. And then it says if you encounter a value in the array that's greater than 5, break out of the loop. Well, that's going to happen when we hit the value 8 here. And then it wants to display what location that is and what was the value where you broke out of the loop. Okay? Now, one thing you'll notice is that we have an if structure here inside of a for loop. I could have made that a one-line if, but I just showed it in the standard if structure. Okay? So this is called break example. So if we come back over here and I type break example, it tells me that it got out of the loop with the 6th item in the loop and its value was 8, which is what we expected. Okay? So that's an idea of how you use break to get out of a for loop prematurely. And let's bring up one that involves continue example. And so here, what I've asked MATLAB to do with its rand_n function is to give me 5 random numbers, all right? And it's according to a normal distribution with mean 0 and standard deviation 1. And then with those 5 numbers, every time I run this, there'll be different numbers. N will be 5. That's how many numbers we asked for. And then what it says is we're going to go through this with a for loop. And if xi is greater than 0, continue. What that means is skip this statement and go around and do the loop again. If xi is less than 0 or equal to 0, this won't happen, and it's going to come here and it's going to set it equal to 0. So the net result of this is that we're going to get an array that will contain only the items in X that are positive, and if there are negative items, it's going to put in 0 in their place. And in the end, it's going to display that. And this is called continue example. So let's run that. Come over here and look. And you can see that we had 5 random numbers, and it looks like the third one was negative. So it zeroed it out. Now, because it's a random number generator, if I do it again, we get a different result and a different result. And each time through, it has filtered out the negative items and just placed 0 in their place. So this just gives you a simple example of how we can use the for loop with the continue statement to get out of a particular iteration and go on to the next one. Okay? So that's that. And then the next example of the for loop, and then we'll go back and review slides, that I want to look at is when we have one for loop inside the other. And that's called nesting. And so let's look for a script that does that. There's one called nested loops example. So here we have an example where we are creating a matrix. And in this case, the matrix is 5 rows by 5 columns. And we're going through with an outer for loop with I. We'll say that corresponds to the rows of the matrix, 1 through 5. And then the inner loop goes j equal 1 through 5, where j corresponds to the columns. So how this works is for I equal to 1, first row, it does j 1 to 5, columns 1 to 5 going across the array, and it sets the value of a I sub j equal to this particular formula. Now that happens to create a famous matrix, which is called a Hilbert matrix, but that's really neither here nor there. And then when we're done, it displays the value of A when we're finished. So if we run that and come over and look, here is our 5 by 5 matrix, and it shows up like this. And it turns out, because of the way it's calculated, you may recognize that this is a symmetric matrix because items either side of the diagonal have the same value, okay? So it's a symmetric matrix. And so that shows you nested loops, one within the other, and that's another variety of using the for structure. Now we're going to move on, and let's go back and take a look at our slides and review. So this was our use of the for loop to compute the MAD, as we showed you, by going through and doing it one item at a time. And then we emphasized that many times you can collapse this into a simple vector operation using the capabilities of MATLAB and make it much more compact. So instead of these 3 statements, and in fact the n equals statement, we can replace that with a single statement here. Okay? So that was our 2 MAD examples. And then we had our example using the break command and one using the continue command. And you'll notice here it knocked out the middle 3 values because that time through they came out being negative. Okay? And the final one we showed was doing the one for the Hilbert matrix with nested for loops, nested loops example. And this shows the code for doing that. It happens that when I saved this, I saved it in a file called Hilbert matrix, but in our case it would be in this file here. So that shows that. So now we move on to the last structure that we're reviewing here, a type of repetition structure, and that's more general, and it's called the while loop. Now, I will mention that the while loop in MATLAB is not really the best example of doing general repetition structures, nor is the same type of a loop in the Python language, and the one in Excel's VBA language is actually superior to both, but we can make them all work. So the simplest example of the while loop is we have the statement while with a condition, which evaluates either to true or false. So while this is true, we execute these statements and come back and evaluate the condition again. And eventually we hope it's going to turn out to be false, otherwise we'll never get out of this loop. And we make note here that we can use the break and continue statements in this structure also. But the way that we sort of adapt this structure to our general needs for what we call the general loop structure is we started out with the statement while 1. Now 1 in MATLAB means true, 0 means false. So if we do while 1, that is always going to evaluate to be true, which means that we're going to be in this loop forever, except that somewhere in the loop we put an if statement with a break that gets us out. Now what that does is it allows us to have a very general structure where we have while 1, we have a number of statements that always execute, call them pretest. Then we test to get out or not, and if we are not getting out, we have post-test statements, okay? Now we use this structure a lot in programming and especially in numerical methods when we don't know how many iterations of the loop is going to be needed. When we use the for loop, we have a general idea how many times we're going to execute the loop, with the exception of getting out with a break statement. With this structure, we don't know how many iterations are going to be required before we break and we get out of the loop. So let's give you a good example of that with the numerical method to solve for the root of an equation that you probably heard of before, and it's called Newton's method, okay? So let's come back over to our editor. And let's go looking for a script which is called while loop 1. Okay, so here we are. Here, what we're doing is we're showing you how to use the original while structure to accomplish this. And then we're going to show you afterward how to use the general while to accomplish it, which is what we recommend that you use. So what we're doing here is we're solving for a root of this particular equation in x, all right? So you can see it's got 1 over a denominator term plus 1 over a denominator term minus a constant s, and it involves q, r, and s, and we set the values here. The other thing we do is we give it an initial estimate for the root, and then we preset an error term equal to that value of x. Then our while loop says that we're going to continue this loop as long as the x error term absolute value is greater than 1 times 10 to the minus 7th. And then in typical Newton's method form, and we'll review this again in the next boot camp, it computes the function value for our current value of x, and it computes the derivative formula for this function for our current value of x, and then it gets a new estimate of x by taking the old one minus the function value divided by the derivative value. Once it has the new value, it calculates the error or the amount of change from the old value, gets that, then it takes the new value, assigns it to the x, and starts over again. And we hope that as it goes through, this x error value becomes smaller and smaller, and eventually it stops when it's at 10 to the minus 7th, because we say x new and x are close enough together that they represent the solution. Okay? So if we run, let's come back to our command window here. And if we run this, we see that it converges on 1.1335, okay, as the solution. So that's the use of the while loop, where you're testing the condition at the front end of the while loop. And it doesn't fit the needs of the general while loop, so we're going to show you the general one now applied to this exact same situation, and that's the file called while loop 2. So let's come down here. Here's while loop 2. And this, again, now we use while 1 and end. So that is stay in the loop forever. But what we do is we take our test and we put it in the middle of the loop, and then use a break command to get out of the loop. And then we have our pre-test statements here and our post-test statements here. Now you will find many situations where the earlier version of the while loop does not work well, and it's really to your advantage, and it may be the only way of doing a general loop, is doing it the way we've illustrated here. You'll also note that I could possibly have two tests inside the loop with break exits, and either one of them could get us out of the loop. So if I do the while 1 and I execute that, I'm hoping we get the same answer, and we do. Okay? So that completes this part with program structure. And now we're going to go through and we're going to review with you in fairly rapid fashion a whole series of examples of using the plotting capabilities of MATLAB. And one of the reasons we go through these fairly quickly is that we want to give you examples that you can go back to. And you can look at the slides for this boot camp. You can come back and you can review the video as you need to, as you come up upon needs to create plots of different forms in MATLAB. MATLAB's plotting capabilities are far more than we're going to illustrate here, but we'll stick with the ones that are most useful, all right? So the first one, I'm just going to do a little script here, and I'm going to say that random numbers equals RANDN 5001. So this is going to give me 5,000 random numbers, and then I'm going to say plot them all. All right. Let me save this script as plot random. And let's just run this. There it is. Not very interesting, perhaps, but it shows of plotting the 5,000 numbers that's along the x-axis. Shows they're all within plus minus 4. This is a normal distribution, standard deviation 1, mean 0, and it shows you that most of them are included in the range of plus minus 1. So that is a very simple plot, and I'm just going to, you'll notice it's provided in a separate window, and I'm just going to get rid of that. And So that's not perhaps very interesting. Now what we're going to do is we're going to proceed and take a look at plots that are a little more interesting and have more features. So I'm going to open a script which is called humps plot. And we're going to add a little bit to our plotting capability here. First, I'm going to create an array going from 0 to 1. And since I don't have a third argument, it's going to be 100 points, equally spaced between 0 and 1. And then I'm going to put all of those into a formula to compute a corresponding array y. Now, whenever you do something like this, you have to be very careful to use array operations where MATLAB would try to do a matrix operation and get you in trouble. So you will notice here where I have 1 over a denominator, I have used period divide because I've got a vector in the denominator. So I want it to do operations item by item. Also, I do x minus 0.3 and I'm going to square it, but I want to square it item by item, so I have to use a period and a caret. So you'll notice that I use those operators twice to get an array y, and then I plot y versus x. So here we've given it an x-axis values to plot. And then you can understand the following 4 statements. Grid, x label, give it a label for the x-axis, 1 for the y-axis, and 1 for the title. So if I run this, this is what the result looks like. And you can see that it has, it's given me a curve which is blue. I can control that. And the line style, it shows the grid, shows my axes. It has scaled the y-axis automatically in order to fit the numbers. It's possible for me to force a particular scale for that, but I've accepted that here. So that is a little more to a plot, and I'm going to just X that out, of just a series of y versus x that we like to show 100 points because when we run it, it ends up looking like a continuous function, even though it only corresponds to 100 values here. All right, and since it's an analytical equation, we like to show it as a line and not with any markers. But then we can have data that actually correspond to visual measurements. So if I open here another file, try to find it here. It's called data with markers plot. Sorry about that. Okay, here we're now working with data, and we've got an array of temperatures in degrees Celsius, and we've got values for viscosity of water in centipoids. And so what we want to do is plot these, but we're going to, let's come back to our MATLAB window, but we're going to plot them in a particular way. So now we're adding some features. The last 4 look familiar: grid, X label, Y label, and title. But I'm plotting viscosity versus temperature, and then I use some codes in apostrophes here. S corresponds to using a square for the data. M corresponds to using the color magenta, and the dash corresponds to connecting the squares with straight lines. So when I run this, I get a curve that looks like this, and even though it doesn't look like it, the lines in between those squares are straight lines. But that gives you the idea of how we can plot data with markers and connect them with straight lines. If I, for instance, get rid of that and get rid of that dash and run it again, I only get the markers, right? And then if I come back and change the M to a K, which stands for black, and run it again, I get black squares. So a lot of ability to customize here, and that's an example of how you can do that. Now, another thing I'll point out here is that when we have a long line of a script line, we can continue it on to the next line by using an ellipsis, that being 3 periods. But when you do that, leave a space before you do the 3 periods, and then you can continue it on to the next line. Okay? So another thing here is if I want to know, well, what are all those codes that I can use for different symbols, for different colors, for different line styles? Well, one way of doing that is coming back over here and typing help plot. And this gives you a lot of information about the plot command. All right? It just goes on and on. But up in here, it gives you tables which show you the different colors, show you the different marker styles that you can use, and over here, show you the codes that you can use for different line styles. And I use just a hyphen or dash, and that was for a solid line. Okay? So you can do that. Another thing you can always do too, and it will tell you, is that you can go documentation for plot, or up here, you can ask for help on plot, and it will take you to a browser, and you can do plot for 2D line plot, and it will give you a lot of information that you might want to use. Okay? So that's a little bit on taking it a little farther. And then we're going to do another example where we get involved with a logarithmic scale, okay? And so let's bring that up. Log plot example. Okay, so now we're adding some additional features to this script. What I am doing is I am setting up to load a set of values for the vapor pressure of sulfuric acid, and I am reading that in from a text file. Now, we went over the using the fscanf before to do this. The other thing that we are doing here is we're making note that there are actually 2 items on each line of my text file. So that's why I set up this size argument where I have 2 items, and then I say, as far as I know, I don't know how big this file it is, so I just say it could be infinity, but it's going to be less than that. So I have that in a text file, and then I read it in, and it brings in my pair of values, in this case of temperature and vapor pressure, and they are in a long row array. So I transpose that into a column array, and then I extract the temperature values as the first column, all rows, the vapor pressure as the second column, all rows. And so that's just getting my data in. And then it turns out that the most advantageous way to display the data is with a semi-log plot, where the log is applied to the vapor pressure values. The main reason for that is that the vapor pressure values in the array differ, I think, by a factor of about 500,000 from the smallest value to the largest value. So I do a semi-log y instead of plot. And here I'm just saying use black and grid and titles. So if we do that, we get this. And it gives me my semi-log scale and semi-log grid horizontally here. And then it gives me my temperatures for this particular array. And that looks like a very presentable chart using a log scale. And there you can use a semi-log x in case you want to apply the logarithm to the x values, and you can use a log-log function if you want to apply logarithm to both x and y values. Okay? So that's a little bit on a log-log plot. So let us now take a look at something that involves in plotting multiple lines, all right, instead of just one line. That's a good example to have. So let's open one for salt solutions here. And this is a good one that we have the script so we don't have to type in all these values, although we could have read them in from a text file. So what we've got is density of salt solutions for 4 different temperatures. And it's in an array where the columns correspond to the temperatures 0, 10, 25, and 40 Celsius. And the rows correspond to weight percent 1, 2, 4, 8, 12, 16, 20, 24, and 26. All right? And this is at 20 degrees Celsius. So what we would like to do is I would like to plot this with a separate line for each temperature. All right? And since I have a separate line for each temperature, I would like to have a legend that indicates which line is which. So I say plot density versus weight percent, and then do these, which are normal, and then I add a legend where I put in 4 string or text for the legend and indicate that I would like to locate this in the northwest corner of my plot. So if I do this, I think the plot should be there somewhere. There it is. So here, if it had put the legend in the upper right, it may have overridden some of these curves. But it shows the curves, all right, the top one being for 0 degrees, the bottom one being for 40 degrees. So it shows essentially the density going down with temperature, but it shows a pretty dramatic change in density for changing the weight percent from near 0 up to over 25%, going from water up here to 1.2 grams per cc. So that's an example of using multiple curves, plotting multiple curves, and using a legend, okay? All right. So we've got a few more to do here just to show examples, and then we'll move on to the last part of this particular screencast. The next one I want to consider happens very frequently, and it is when you want to plot two curves and one of them has a really different scale from the other. So let's open one that's called Twin Axes Plot Example. So what I'm doing here is I'm reading in another text file, and this one has 3 entries per line, as shown in the size here, and it's a file called furnace-data.txt, and the R means reading it in. This is very similar to before, and then transposing the data, and I'm extracting a time, I'm extracting a fuel rate, and I'm extracting a CO2 concentration, percentage CO2, and this is for the flue gas of a furnace. And then what I want to do is I want to plot this on a plot where the fuel rate is on the left and the CO2 is on the right axis. So that's where I use this y-axis command with the keywords either left or right. And then I follow each by a plot command, and then I can do my labels, and then when I want to do what was last was right, so it puts this on the right side, then I do left, and it puts this on the left side. So that when I run this, it comes out looking like this. And you'll notice how it's neatly color-coded, so I really don't need a legend. I could make one, but I don't really need one. And you'll notice that the normalized fuel rate is in the range of -3 to 3, but the flue gas percentage goes from 44 to 62. So that's why it's been convenient to use a left and a right axis for this. And you may be familiar with creating plots like this with Excel, where you can specify which goes on the right and which goes on the left, or secondary and primary axes. All right? So that's an example of doing that. You may need to do that at some point in time. So the last things we want to show here are first creating three-dimensional plots, all right? So let's go back to the slides and bring ourselves up to this point and show you what documentation is provided there. So this was our salt plots, and then this is the one that we just created. And these are all, the code of this, these are all available for you with the files that have come with the bootcamp, okay? So let's come back to our editor and look for a file that is a contour plot example. So this is a contour plot. And we're doing a very simple one here, but what we're saying is that for x, we're creating a set of values between -2 and 2, and we're 9 points, all right, between -2 and 2. And then we're creating a y array exactly the same as the x array. And then what we do is we create something called a mesh grid. And what the mesh grid function does is it takes as the x values along the x-axis and the y values along the y-axis, and it creates, in this case, 9 by 9 matrices of all the corresponding x and y values, all right? So that correspond to any place on the grid of X versus Y. And these are two matrices that we then use in a formula here to calculate a third variable Z or Z. And one thing we note is that we're using X and Y in an item by item or array type formula. So when we get to something like X squared, we use dot caret, Y squared dot caret, and X times Y dot asterisk, because we don't want it to try and do a matrix multiplication. We want it to multiply each item in X with the corresponding item in Y. And then we just use a contour command with XYZ. We ask turn on show text, and you'll see what that does in a moment. And we just provide labels for X and Y and also now Z, and add a grid. When we run this, this is what we get. A very nice contour plot. And it labels each contour just like a topographical map in terms of what the value of Z is. And we sort of tell it's got a maximum here at 0 and 0. Okay? So that's what that looks like for doing a contour plot. Now, in a very similar way, we can bring in another file, which is called surface plot example. It's the same basic setup all the way through, except we do surf instead of contour. And when we run that, we get a contour plot, all right, which is 3D type of example. And then so that's what that looks like. Throw a C in there, what we get. If we do a C after the surf, we get, it shows contours on the bottom of the surface. Just sort of shows us what that looks like. Now the surface plot is not the greatest for finding values, although you can find yourself on different places on the surface, and it will tell you where you are as long as you're at an intersection. Okay? So that is using the surface plot. And then you can actually, instead of using an analytical function, you can actually use data to create a contour plot, for example, where it will interpolate the data to give you contours, and it will do that automatically. And that's pretty neat. That's pretty powerful. So if I go back to my salt solutions and do salt solutions contour plot script, the same front end we had before. Now we, instead of doing just a simple plot, we do a mesh grid with our weight percent and temperature, and we put temperatures 0, 10, 25, 40 in an array. So we create a mesh grid with that, transpose it, and then we do a contour plot of density versus our values of our mesh grid for WP and TP, all right? And put that in, add the appropriate titles and everything to it, and it looks like this. So this gives us the ability for a weight percent and a given temperature to come in and perhaps interpolate here or see where we are on a particular contour as we move along it. All right? So that's quite powerful. All right? And then the last couple types of plots are ones that perhaps we don't use that much, but we'll illustrate them with an example so that you can see what they look like. And the first one is creating a bar chart. All right. So let's take a look at creating a bar chart. You might use that, for instance, with a histogram. There's a script called bar chart example. And this illustrates one additional feature of MATLAB. But what I've got here is data on energy supply, all right, from 2019 from different sources. Now, the difference here is that my sources are strings, they're text items. And you cannot put text items into a regular numerical array in MATLAB, but you can put them into something called a cell array, which allows you to put in any kind of items. And it's similar for Python to a list or a tuple in Python. And here I create a source cell array that has the names of my energy values, and then I create an X variable which is categorical, all right, and then I reorder it, all right, according to the source values, and then I plot a bar chart of that and include a grid and some titles. Now, when I do this, what the reorder does for me is it gives me something called a Pareto chart, which orders these from the largest down to the smallest and gives me an idea of, for instance, how hydropower compares to that of oil worldwide in 2019. And you can pick off the value here in exajoules. All right, so that is an example, and you wouldn't have to reorder things in order to make the bar chart. All right, you wouldn't have to do it that way. I'm just sort of experimenting here, but if I comment this particular line out, then what do we get? This comes out in the order, in this case, alphabetical order, all right, is the way that it comes out. So I'll just remove that from there, and that's your example of a bar chart. And in a very similar way, sometimes we like to illustrate something with a pie chart. So let's show an example of one of those. And here again we use a cell array for 6 countries, China through the UK, and then we show the amount of wind power in 2021 in gigawatts. And then we do a pie chart of wind power by country. Notice the order there. And then we run that one and we get a pie chart. And of course, if you get into looking into the pie function, you can find out how you can change the colors, things that you can do by putting entries of numbers within the pie elements. You have other capabilities that you can look into, and you can draw some immediate conclusions. Perhaps China is a little bit ahead of us in wind power generation, right? Okay, so let's roll through that on our slides, and then we'll finish with another feature of plots having to do with multiple plots, and then we'll go on and we'll look at creating functions. Okay, so this was showing what happens when you take X and Y and do a mesh grid, and it creates this type of thing with the mesh grid, all right? And you can see that for the X mesh, the same values are available vertically, and for the Y mesh, the same values are horizontally. So if you pick any location here and compare it to a location, you get the appropriate paired values of X and Y. And then this was what it looked like for the contour plot. This was the surface plot, and I threw in a C here to throw a contour on the floor below that plot, just to show you that there are other things that you can do with this. And then this was the doing the mesh, doing the contour plot where you're dealing with data, all right? The salt solution data. And here our bar chart in a Pareto formula, and here was our pie chart. Okay, and then we move on, and the last thing we're going to talk about is figure windows. And what we use figure windows for is when we, in particular, when we would like to add multiple plots. That's the typical way that we do it. But way that we do that, you'll notice, is that if I create a plot in MATLAB and I then use another plot command, that will generally wipe out the first plot and present us with the second plot, okay? Now, if you want to plot two things and have them show up on the same plot without wiping out the first plot command, you can use a command in between them that is called hold on. And if you use hold on, subsequent plots will put the curves in the same figure, all right? So if you want to create and retain subsequent plots in separate windows, you can use the figure command where you say figure and then you put like 1 in parentheses. That creates a window for the first plot, and figure 2 creates one for the second plot, all right? And so you can do it that way, and then you can actually remove a figure window with CLF command and all figures with the CLA command. A little bit of details for you there. So if I come back to an example called figure window 1 here, what this does is it opens up and it creates the data from our furnace file, and then it plots TS fuel, and then it uses a generic figure command to plot TS CO2. This way it will retain both plots. Let's see if we can do this. So there's the second figure, all right, which is the CO2 figure. And then if I move this around, there's the first figure, which is the fuel figure. So by using the figure command, we get and retain both in different figure windows, okay? Now, if I were to remove this figure statements here, it would plot the first one, and then it would plot the second one and wipe out the first one. So that's an example for you there. All right. Now, another thing I want to discuss with you is a little bit about working with the uh, plot window, and it looks like I lost that. So let me come back around and run it again. So here's my plot window. So sometimes what you want to do is you want to zoom in on a portion of the plot, and you can do that with the little magnifying glass with a plus up here, and then you can create a window and it will zoom in to that part of the plot. All right. And then up over here, there's a little house which says restore view, and that takes you back to where you were. All right. So again, if we click this guy and come in, we can take a particular look at this, and then we can restore it. Okay? That kind of thing. The other thing that's useful is, what do you do when you have a figure and you want to copy that figure to a PowerPoint slide or a Word document, etc.? Well, one thing that you do there is you go to Edit, and then there's an option called Copy Figure. So when you do Copy Figure, it puts that figure on your clipboard and you can paste it in wherever you would like. And then the final thing I want to illustrate to you is how you can put multiple plots in a figure window. All right? That is a useful thing to do under a number of circumstances. So let us come back over to our command window and our editor, and we will look for a file dealing with multiple plots. Figure window example 2. All right. So this is pretty repetitious code, and that's why I have it in a script for you. Essentially what we're doing is we want to make 4 plots here. And they're plots of the sine function, cosine function, hyperbolic sine, and hyperbolic cosine. All right? For x, 100 points between 0 and pi. So the way that we do this is we start out with a subplot statement, which states that we want a figure window with 2 plots in it by 2 plots. We want 4 plots in a figure window, and then we put in an index that is, in this case, is 1, and that corresponds to the subplot in the upper left-hand corner. And you count the plots across rows. So you've got 1, 2, 3, and 4. So what we do is we do subplot, we make our plot, we do the second subplot, which will be the upper right, plot of the cosine. Third one is the one in the lower left, hyperbolic sine. Fourth one is the one in the lower right. And you can do this, you can have only 2 horizontally, 2 vertically. You can try to compress things and end up with 5 plots by 5 plots, maybe hard to see. But when we run this, we get our 4 plots fit nicely in the figure window side by side. Okay? So let's just review that on our slides. Were the figure window 1 and figure window 2 that we showed you. This had to do with how to zoom and capture that, and then how to copy figure off the editor window, how to restore the view of a zoom, all right, with the little house over on the right, and then how to create a figure window with multiple plots. Good. So let us move on and discuss how to create functions in MATLAB and then make use of those functions. So we will come back over to our editor, and I'm going to start with a blank script, and I'm going to put in some code first, and I'm going to start with the word function. Now that means we're not dealing with a generic script here, we're dealing with a function that's going to be used elsewhere. And then I'm going to do a conversion from Cartesian to polar coordinates. So we'll put in brackets r and theta for radius and angle, and then I will call this cart2. Then we're going to have arguments which are our Cartesian coordinates x and y. And then you're going to do this fairly quickly. The radius is equal to the square root of squares then the angle in radians is equal to the arctangent, and I'm going to use what's called the 4-quadrant arctangent. On the values of x and y, and that's it. All right. Now, it turns out that you can embed functions in scripts, other scripts, but it's really preferred to save the function, and when you do, it automatically gives it the same name as the function name, cart2polar. So I save that, all right? And then in a script elsewhere in another editor window or back over in my command window, I can come in and I can say cart2 polar -3, -4. And the answer is 5. All right? Now, that didn't work because it gave me the radius and it didn't give me anything else. And if you remember, coming back here, whoops, let's find that function again. It actually says that it's going to return 2 arguments, r and theta. So let's come back to the command window and edit this guy and say that what we really want is radians and angle as the result of this. And then let's try to run that. And now we get a radius of 5, which is 3 squared plus 4 squared, 25 root, all right? And then the angle is -2.49. And then if I prefer, I can say th in degrees is equal to, using a built-in function, rad to deg of th, and it's -143 degrees, all right? So this gives you a little bit of an idea of what the syntax is for creating a function, and you use these a lot, all right? Generally, in some cases, as you'll see in the next boot camp, you use solving functions in MATLAB that require you to create a function that you supply to the solving function. And we don't get to that here, but you'll see it a lot in the next boot camp. All right? So that's what the function looks like. And then the last thing that I want to show you is a script where we have used a lot of comments. And this is something that we really suggest. Many of our simple examples haven't really required it, but we're going to look at a script that's called Peng-Robinson methane example. And this is a longer script, so it doesn't fit in one screen. But what you will notice here is that we've added a lot of comments at the front. We've started out our script by clearing the workspace and the command window. We've declared a variable R for the gas law constant as a global variable, so it can be available to other functions. Given its value, you'll notice as we go down through here, we add comments with the percent sign to show the units used. We're calculating the pressure for methane here with Peng-Robinson. And so we have the molecular weight, kilograms per k-mole. We have critical properties in kelvins and pascals. And then we have the acentric factor for methane, usually in omega, but we use a W here. Temperature, we put in 700 kelvins, excuse me. Specific volume of 0.1. It's quite compressed. And then we have a reduced temperature. And then we go through the Peng-Robinson parameters that you may have well seen in your thermo class, and go through the calculations to compute the pressure. It comes out in pascals, we convert it to kPa, and we display the result. So this just gives you a little view of a more extensive script where we use a lot of comments, helps somebody else to understand the script, helps you to understand the script if you go back to it after a period of time. And if we run this, our command window, it shows us that in this case, we're at 58.2 kPa, which is not really that high in terms of a pressure. Okay, so that is what that looks like. So let us come back to our slides and finish this up. This gives you the general idea in terms of how you put together a functions with out arguments and in arguments, and then you have code using the in arguments, and you have to assign a value to each out argument at the end of the function. One thing you'll notice is there's no end statement at the end of the function, and you save the function as function name.m, whatever that function is. And this is the simple example that I illustrated to you. And again, here I used cart to polar with underscores. That's neither here nor there. Saved it as that .m, and then showed how to use it in the command window. And it could also be used in other scripts as long as it's available. So this slide here just reviews what I already illustrated along the way of different ways to operate in the editor, to run the script itself, and to save it when it appears needing saving, single-stepping the code to observe what happens in the workspace as you go through the code. As we'll see in the next boot camp, there's ways to do things like put in breakpoints, things like that. And then this was the code for our Peng-Robinson calculation. And that brings us to the end. So here we are, and We're going to be moving on to the next boot camp where we use MATLAB to solve many different problem scenarios which occur in chemical engineering. And we hope that you have made your way through this. You have the slides available. You have the files available. You can always contact me, david.clough@colorado.edu, with any questions that you have. And at this point, we will call this to a close.